hopefully 3 minutes, to talk about neural networks. I'll skip these terms, but you know, some of these are related, very similar. Weights. I'll actually talk about weights and show how they are different from logistic regression. It's kind of a big difference though. Also have bias activation. Now we start to and gradient descent, but we start to introduce mini-bench because the model is getting complex. And so these are the techniques that will be helpful, right? But what I want to do is to compare logistic regression with neural network and to kind of to show, to give you a sense of the scale of change that's coming. You know, it's like, you know, Plants versus Zombie, a big wave is coming. So how big is it? So the structure that in logistic regression, let's say LR, we have this denoted as 1, and then we have so x1, x2, xm. So we have m number of input variables, and then we have these. You know, these are weights. You know, we use a box. These are weights, and then we have a circle. This is more, you know, of a net input and then activation. I'll just combine them, and then you have y to make predictions. Here the weight, we say weight W0, right? W0 is a vector that has a W0, and then the rest has length of m. So together, it has a length of m plus 1. So that's a vector. And you remember that when we update the weight, then when we calculate, when we update the weights, we update the bias and the rest of them separately. That's the way it is. And these are the only weights. When we do backprop or when we do gradient descent, we have the delta weight that has the same shape. M plus 1 elements here. And that's basically all that we're managing here, right? So that's logistic regression. So I'm going to draw what a neural network will look like in same terms. Let's see. So we begin with the same data set. It's the same. This is intercept basically that connects with the bias, and we have x1, xj, xn, same thing. And now we have a hidden layer. From a hidden layer with x number of hidden units.
Do you have xj on that one too?
Xj.
They're always xj?
Yeah. Same. Yeah. Let's say they are the same. We have, let's see, a hidden layer that has, I use k. So, but there's no letter to denote the node, so I'll just use letters. So 1, k, and the maximum is d, yd is hidden, let's say, that's y. So I, j, k, and we'll continue. And also we have a kind of special, as 1, which is the not bias, which is also the intercept, but here it doesn't have weight. So let's say, for now, ignore that. Similar to previously, we have, this is 1, right? This is the first hidden node. we have these connected, but instead of all going to one, like in here, they all going to multiple. To every hidden node in the hidden layer. You can imagine.
So is that like that activation or is that like that Y?
Not yet, no activation yet.
None of that.
But every one of these has activation. But we don't have yet Y yet. We're not there yet. So
Are we before or after?
not here. Similar to here. Yeah. And so you can imagine this part. These are the weights. These are one part of the weights. And these we call W, H, or H hidden. So these weights work for the hidden layer. Okay, and before we have every input variable connected with just one node, right? And now we have every input variable connected with every node. So you can imagine the scale. Now this W is not a vector anymore. It's a matrix. You know, these are filled with numbers. This is matrix. And guess how many rows are in this matrix? We used to have n plus 1 as the number of elements in the weight vector. Guess how many rows are here? Nope. M. Let's say M. And how many columns are going to be decided by how many hidden nodes? Not including that one. That one is for the next layer. Yeah. That depends on how many hidden units we specify. Here it's D, right? D is the number of hidden units. So M by D. M is actually a good guess. I was guessing you'll guess M plus 1 because here it's M plus 1. But it's actually not M plus 1. It's M. M correspond to the number of input variables there. But still, why did we have one more previously? We have a bias. We don't have bias here. So we will actually have a bias vector in addition to the weight. We have bias vector for the hidden layer. And this one is a row vector actually. And it has number of elements that's the same as D. So you can imagine you can move this over here, stack on top of that weight matrix. It becomes M plus 1 by D. That completes all. So basically, we have the number of elements M plus 1 times D, right? That's the additional weights that we have now here. If we have 6 layers, you're increasing the model by 6, the number of complexity here, right? And that is for the hidden layer. We basically finished talking about it. And then now we have the output layer. We have the output layer, and in logistic regression, we only have one. That is kind of the output layer, right? In logistic regression, we only have one, but we want to make it general in the sense that we can use this model to make classification in case there are more than 2 categories. You know, cat, dog, and pig. You know, recognizing the animal in the picture, it can be hundreds actually if the model is complex enough. So this output layer can have multiple as much as you have the number of categories to recognize. Right? So if it's binary, then we use 2. And the 2 is kind of redundant in this case because using 1 is sufficient, but we learn how to do that so that we can generalize to more labels. And in here, the same process, you have this bias and, you know, everything connected. And the same process goes on again. Bias of H, and now we have weight of output, and we have bias of output. So imagine a forward prop, we will calculate, we'll use the weight matrix and bias vector to calculate hidden layer values, net input for hidden layer. We'll do activation. And after that, we'll calculate the net input for the output layer by using the activated value from hidden layer with the weight of the output and bias of the output to calculate net input of the output layer, and then do activation. Then we can kind of make predictions. And now comes the back prop. We have to do, many more steps to know how the gradient will propagate from the output back through the hidden layer and then back through the first layer of the weights. So that's what we're going to do in the next 2 weeks. Okay.